I hope everybody is fine, and in this video I'll be looking for applying the non-degenerate perturbation theory over the simple problems, and the choice is here to make things simpler. The choice is that what we will do is we will choose a problem in which we have a particle, and this particle is in an it's in a potential, and the potential wall is infinite at x equal to 0 and x equal to L, and we will go through this problem step by step using time independent perturbation theory for a particle in a one-dimensional infinite potential will with some perturbation, as defined, say hp of x. Oh, sorry, it has to be perturbation hp equal to, say, v naught of x. So what's the statement of this problem is that the potential inside is 0 between 0 and L, and it's infinite otherwise. So the unperturbed Hamiltonian in this case will be h naught, and the perturbation that we have assumed here is hp, and this hp is v naught of x, where this v naught is basically a small constant. So v naught is small constant, and we will solve this problem using non-degenerate perturbation theory. So obviously we will have the unperturbed Hamiltonian, and we can see that the potential between x equal to 0 to L, v of x is 0. So how would our unperturbed Hamiltonian look? So our unperturbed Hamiltonian, which is h naught, is basically the summation of kinetic energy operator and potential energy operator, but the potential inside the well is assumed to be 0. So this h naught will be simply minus h bar square by 2m d2 by dx2. And with the boundaries, if you think about the boundary conditions, we have psi of 0 equal to psi of L equal to 0. This is because the wave function must vanish at x equal to 0 and at x is equal to L. Now, we have already solved the problems like this, like the problem of particle in a box, and we already know the solution of this unperturbed Hamiltonian, and we know about the energy eigenstates, and we know about the energy eigenfunctions. Now, the solution to the time-independent Schrodinger's equation for this h naught, which is well known to us, is psi n of x equals under root of 2 by L sine of n pi x by L, where this n that's incorporated here is an integral number like 1, 2, 3, and so on and so forth, corresponding to all those unperturbed energies are. What are those energies? That is En naught is, we have n square pi square h bar square by 2ml square. Now this is the case. Now these eigenfunctions form the complete orthonormal set. That's all understood from our previous knowledge. Now, what we want to calculate here is we want to calculate the first order uh, energy correction, and the perturbation is given. So what we want is first order energy correction, right? And this first order energy correction in non-degenerate perturbation theory, which we have already calculated, is En1, and this En1 is nothing but psi n0 Hp and psi n0. Now we have Hp. What's that? That is V naught of x. So En1 will be the matrix element of psi n naught, V naught of x, then psi n naught. Now we have incorporated here Hp equal to V naught of x in the context of the given problem. So what we need to do here is to compute this matrix element. And if we have to compute this matrix element, this will be psi n naught and V naught of x psi n naught. And V naught is a constant as we have given it, so V naught is out. So you will have integral 0 to L psi n naught of x. Then we will have left with x, and then psi n of x and dx. All right, so this is our matrix element, and we can substitute. We can see this psi n of x is equal to this thing, so we can substitute this in our integral, in our matrix element, and see where we reach from here. So what we will have is we will have En1 equal to V naught integral 0 to L, and then you will have sine n 0 of x. Since we have sine n of naught of x, it does not have any complex thing associated with it with this in the solution of Schrodinger's wave equation. So we can simply multiply psi n naught of x with psi n naught of x. So what we will have under root of 2 by L sine of n pi x by L whole square. Then you have x, you write that out, and then you'll have dx. This is how it will go. Now we can proceed from here. So this is V naught is out, so square and root will cancel, so 2 by L is out. So what you are left with is 0 to L. This is sine square of theta, and for that I can write 1 minus cos 2 theta, that is n pi x by L, this whole divide by 2, and then you have x, and then you have dx. This is how we will go from here. Now what we have is we can separate down the two integrals here, like the first one will be as we have two integrals here. So the first one will be this is V naught 2 by L. Keep it like this. Then I have integral 0 to L. Then x will be multiplied with 1, so this will be x by 2 and dx. And then we will have minus integral 0 to L, and we will have I think here I have done a mistake. This is x by 2. So this is x by 2, and here I will have cos of 2 n pi of x divide by L, okay, and you can have 1 by 2 outside, and then we will have d of x over here, and I'll close this. So I have two integrals. Okay, this one we better understand what is its integration will give us x squared by 2, and this one we will have to integrate. Okay, so I would like to write down it for the sake of simplicity. This is over en1 is v naught 2 by L times 1 by 2 is common, and then I will write down I1 plus I2, where I1 will be my integral. I'd like to call this, say for example, this is equation A. So what is my I1? I1 will be 0 to L x squared by 2 dx, not x squared. Okay, when you integrate it, you will get x squared by 2, 0 to L. So this will be L squared by 2. So this is the evaluation of the first integral. That should be the case. Now let's go with the second integral. Now what is our second integral is I2, and I2 is how much? Okay, it has 1 by 2 with it. Okay, I'll write down my integral, that is 0 to L. Then it's cos 2 times n pi x by L. Cos 2 times n pi x by L, then dx. Okay, and x. So this thing is multiplied by x. Okay, so this is our integral. So here we will certainly have to use integration by parts, and for that what we will do is we will choose our functions, like if I choose u equals x. I don't think there's no need to go like this. The best thing is to integrate it. Okay, so how do we integrate? We have u as its, and then we will have the integration of v. So what is u? I will take x as u. Then we will have the integration of v. So integration of cos theta will simply give me sine 2 n pi x by L, and then the internal derivative of this angle will be divided, and what will be that? That will be 2 n pi by L, and what will be the limit of this integration is from 0 to L. Then minus, we will have integral of 0 to L, the differentiation of x. The differentiation of x will give us 1, so I'll not write that. And then you will have the integration of the other, this cos of 2n pi x by L, so that will be sine of 2n pi x by L. This is divided by the internal derivative, that's 2 pi n by L. So this will be it, dx. All right, so we can write down here, this is x, this L will go up, so this is L by 2n pi. Then we will have inside sine 2n pi x, and divide by L from 0 to L, then minus, okay, this L will go up, so this is L by 2n pi integral 0 to L sine of 2n pi of x by L and dx. All right, so this is our situation, and we can see on this part of this integration, and we can see it easily that for the lower limit it's 0. For the upper limit, for x I have to replace by L. L and L will go, so sine of any pi is 0. So this thing is equal to 0. Okay, so we have got rid of it. So now let's go with the remaining part of our integral. And what's that? So we got to integrate this again. Okay, when we integrate this again, what we are going to get, is minus L by 2n pi. Then integration of sine is over cos, that too will have minus cos. So this is minus cos of 2n pi x by L. Then you will have divide by the internal derivative of this will give us 2n pi by L from 0 to L. This is how it will go like, okay? So what we are going to do is we have this this will give us this L will go up, so this is minus L square by 2n pi whole square. Okay, let me write it like this, and then inside we will have minus cos 2 n pi L by L. Then minus will give us plus, then we will have cos 0. So this L and L will go, and what we'll get is minus L square by 2n pi whole square. So this will give me minus 1, so this will give me plus 1. The 2 will go and you'll get 0. So that means this I2 that was over there, this I2 is equal to 0. So so what will be our overall case? So for I1, I think for I1 we got L square by 2. Okay, and now we can go back to our equation. So this is our equation. So I will use En1 V0 2 by L. This 2 and 2 I should cancel here. So V0 by 2 times L square by 2. Okay, because this I2 has come out to be 0. This I1 has come out to be L square by 2. Yeah, that was it. I1 was L square by 2. Okay, so this way I can put it there, I can put it there. So what will be my En1? The first order correction will be V0 times L by 2. So what we see here is this first order energy correction is same for all the values of n, for all values of n. It is same for all values of n. And what is that? That is En of 1 is, that is En of 1 is V0 L by 2. And this should be clear. Now, for the same problem, let's look for the first order wave function correction. And we know from our lectures on the correction to the wave function in non-degenerate case, we have the first order correction. First order correction. Okay, first order correction of what? Wave function. Call it wave function or eigenvector. So what's that? That is psi n of 1 of x is sigma m not equal to n, the matrix element of psi m0 hp psi n0, and divide by en0 minus em0 times psi m0 of x. All right, so this is our situation. So we would like to compute our matrix element here. So let's compute the matrix element. If we see this matrix element is it is psi m naught, then we have v naught of x, then psi n naught, and this is simply v naught 2 by L integral 0 to L, then sine of m pi x by L times x, then sine of n pi x by L times dx. Now, this integral will vanish for most of the combinations of m and n due to the orthogonality between m and n of the sine function, because this is composed of sine functions. But certainly it will yield some non-zero values for some specific transitions. However, calculating will not go into the details of the complex calculations that arise over here. So this is how we can obtain the first order correction in the wave function by actually calculating the matrix element of the perturbation that is invoked for this particle between the walls whose potential is infinitely large, and calculating this matrix element where we have the dependence of m and n. So for most of the values of m and n, this integral will vanish, but it will exist for certain values of m and n, and that will give us the correction in terms of the first order correction to the wave function. Now, so with this, I think I would like to stop here. And in my next video, I think I'll go with another problem based on the same non-degenerate perturbation theory, where we will impose the perturbation in terms of the weak electric field on our unperturbed Hamiltonian, and we will try to see the consequences of killing this, of interacting over degenerate system with an external weak electric field, which is also called as Stark effect. So with this, I would like to say goodbye.